Hello and welcome to the final problem. This is a bit of change of pace from the previous questions. This one is generally on B trees, and it's mostly just a quick mechanical problem and a little bit of the motivation behind B trees. Okay, so we've been looking at binary search trees, all of this worksheet. And if you remember all the way back to the first question, I believe, I was talking about runtimes for binary search trees, or the second question, I think. And here's a question related to that. Why does a binary search tree have a worst case runtime of theta n for contains? And the reason is you can end up with a spindly tree, something that looks like that, and then you have to go do contains and you have to go all the way to the bottom of the tree to find the given element, right? This is n time. So we were talking about how we want our binary search trees to look more like this. We want them to be bushy, because when they're bushy, generally speaking, it's easier to retrieve elements because all the elements exist at a lower depth, right? It doesn't take as long. So you end up with a log n time, generally speaking, to find things in this tree, right? The worst case of find becomes log n rather than the worst case being n in the case of a spindly tree. Okay, so as a result of this, there's a lot of motivation for us to create a data structure that is basically an adapted form of a binary search tree, right? Similar to a binary search tree, but we want something that will enforce not only this property of everything that is less than goes to the left, everything greater than goes to the right, but also something that will enforce that our tree will remain generally in a bushy state, right? That way our searches and stuff don't take as long. That's kind of the motivation behind B trees. That's the motivation behind red-black trees, which are not on this worksheet, but we've talked about and we'll talk about more in the future. So basically continuing on with that, it says give a sequence of operations which are inserted would give you a bad binary search tree. That's just like 1, 2, 3, 4, 5, 6, or 5, 4, 3, 6, or 5, 4, 3, 2, 1. Basically any ascending or descending order, because you're going to end up putting something to the right, then the right, then the right, or the left, and the left, and the left, and the left, etc., and get this really spindly tree. Okay, so here's a B tree with order 3. I don't really know what they mean by order 3. I think they just mean here's a 2, 3 tree is generally what we would call it in this class. And basically, it just wants us to do a contains operation manually. So I'm going to assume that you're familiar with B trees and you generally know how they work. I'm just going to go through the problems here quickly. So how would you look for contains in a B tree? So a B tree is the same thing as a binary search tree, except now instead of just having it being binary, in this case, it's up to ternary, right? You have 3 different children coming out from it, and you have 2 values inside of each node. So the process, though, is going to remain relatively similar. So now we're going to look at contains in 40. So first, we're going to start at this node, which is the root node. And we're going to look through and we're going to say, okay, is 40 in here? And in this case, it's not. So then what we're going to do is we know that 40, if it does exist, is going to be in one of these 3 children. Before, we just had, okay, am I greater than one thing or less than one thing? Now we have 2 things. We say, okay, is 40 less than 24, in which case it would be down here? Is it in between 24 and 72, in which case it would be here? Or is it greater than 72, in which case it would be down here? In this case, of course, it's in the middle because 40 is between 24 and 72. So you're going to go down to this node, basically. And then what you're going to do is you're going to look at this node. You're going to say, okay, here's 30, here's 40. Oop, there's 40. We found it. And we're going to return true. We're just going to stop right there. If this was not 40, but for example, maybe let's say that this was 50, then again, we would say, okay, well then 40 has to exist in the middle. It has to exist between 30 and 50. So we would try to go down the middle, but the middle is null. So at that point, we would just return false because we know we found it's not there. Okay, so this is a binary search tree, basically, or this is a B tree. Notice that it's very similar to a binary search tree in the way you search things. And notice that it also has this log time search when you have a bushy tree like this. And the whole point of this tree is that it always remains bushy. Okay, so now we want to insert 35 into the and draw the resulting tree. I just redrew the tree that we had before down here. It looks a little bit different, but this is the way that I normally draw it. I think it's a lot of work to draw it like this way, but it's the same basic thing. We have as many as 2 different items per node, and we have 3 children on each node. Notice that these children are all null. Oftentimes when people draw B trees like this, they'll draw out the children if they're null, unlike binary search tree where you don't normally draw null children. That's just generally how it works. Okay, so now we're going to insert 35 into this B tree, and we're going to see what happens basically. So we're going to do the same process we just did before, basically when we were finding 40, right? We're going to start by looking at 27 or 24 and 72, and then we're going to say, okay, which way do we need to go in order to insert something? We see we need to go in the middle because 35 is between those 2 things. We go to this node, and then we say, okay, which way do we need to go? We say 35 is greater than 30. It is less than 40. So we know we need to go down the middle again. We try to go down the middle, but there is null. There's nothing there. So then we just insert 35 in this node. However, there's a problem with this, right? This is a 2-3 tree, which means that every node in this tree can have as many as 2 children, or as few as 2 children, as many as 3 children. And once you do this, you now have 4 children, right? Because you have something between 30 and 35, something between 35 and 40, and something greater than 40 and something less than 30, right? And you can't have that. So what we're going to need to do is we're going to need to split this node up. We're going to need to do basically a fix up. Okay, I hope that makes sense. So basically what we're going to do is we're going to take this node and break it up into 2 different nodes. Remember, see here, the problem is that we have 4 different children in this one node. So we're going to break it up into 2 children, each of which into 2 nodes, each of which have 2 children. So what we're going to do is break this node, and then we are going to basically have a node like this and a node like this, right? A node that says 30 has 2 children, a node that says 40 and has 2 children. What are we going to do with the 35? We're going to push it up the tree into the node up here. So it's going to get pushed up into this node. Notice we have something like this now. Okay, so notice how we fixed our problem here, right? We basically split the 2 nodes in half and then took the middle element and shoved it up in the next node. That way we now still have 4 children. One represents, less than 30. One is between 35 and 30. One is between 35 and 40, and one is greater than 40. So we still have 4 children. It's just they're distributed across multiple nodes now. Notice though that we've given ourselves another problem, because now there are 4 children in this top node, right? We've kind of taken the problem we had in the bottom and we've just pushed it up 1 level, but the problem is still there. So we need to just do it again, basically. We do the same thing. This node is now what we might call overstuffed. So we're going to do the same thing. We're going to break these 4 children into 2 different nodes, each of which have 2 children. So same thing. We break up the node. We create a node that represents everything less than 24, greater than 27, less than 72, greater than 72, and we push the 35 up. There is no node to push the 35 up into. So now it's just going to be on its own like this. It's going to have 2 children, and it's going to have 2 children like that. So this is what we're going to end up with basically when we do this. So that's the basic property of adding to a B tree. This is something that you can do mechanically. You'll get very used to this. You'll have to do it a lot because this is, if you can learn how to do this process, this is one of those things on exam that ends up kind of being like 3 points and everything. Okay, but notice what we did. We inserted at the bottom node. We inserted at the bottom of the tree at a node that was not empty, right? Unlike a normal binary search tree, where we just insert at a null node. We insert there, and then we fix up, we push things back up to the top. Another thing to notice is that a B tree grows kind of from the bottom up rather than the top down. With the BST, you increasingly put things at a deeper and deeper depth. With a binary search tree, you start with 1 depth, you put something in that depth, and then only when it's strictly necessary to push something up, you then extend upwards, right? So that's a little bit of the difference. Right, okay, so then this will say what property of a B tree rectifies the problem of binary search trees, such as in 1.1, and why would you not use a B tree? So basically the property is these fix up operations or these self-balancing operations, right? Notice we let nodes get full and then push them up instead of just putting them wherever they fall. So it fixes this problem where we end up with spindly trees, like in a binary search tree. Everything basically ends up bushy, so we can kind of guarantee this log runtime when we're searching for things. We never have n runtime. Another benefit is you can basically add a lot of elements into 1 node, which is nice for a lot of reasons. This is a little bit of a more concrete reason, but you could imagine maybe you have a machine where it's very cheap to read information that is very close to other information. For example, maybe it's very quick to read 75 and then 80 because they're in the same node, but it's very expensive to go between different nodes, right? Traveling between nodes is really expensive. In that case, it's very nice to have a B tree because it minimizes the number of nodes you have to jump through, right? Because a lot of things are on the same level. That's maybe a real world application. That's one of the reasons that databases tend to use this data structure a lot. Why would you not use a B tree? One thing is it's of course just more complicated. In particular, we never actually have you implement B trees in this class because they're notoriously difficult to actually implement in code. There's a lot of weird edge cases. We normally implement them via left-leaning red-black trees, which is something we'll talk about later. But in general, it's the classic thing that more efficiency comes at the cost of higher complexity. And when you have higher complexity, there's always more room for error, more margin for error that presents itself. But anyways, that's basically the answer to this question. That is how you do this. And I hope this worksheet has gone well for you.